Hello students, welcome back. In this particular lecture, we will be building on what we learned in the previous lecture. In the previous lecture, we did non-inverting and inverting amplifiers using operational amplifier. We looked at the differences between them and the advantages of both the configurations. So in this lecture, we will build yet another amplifier called instrumentation amplifier, and we will combine the ideas that we have learned between these two and come up with even a better solution. The research and innovations happens in the similar fashion. There are small ideas each individual comes up with, and then eventually somebody comes in and combines everything together. And this instrumentation amplifier is one great example of such thing. We will also go through a few other circuits like a differentiator or integrator circuit. For those circuits and to understand them, you need some amount of frequency analysis understanding. So what you need to do is you need to be familiar with bodyplots. I understand that some of you may not be familiar with bodyplots, so we are going to have a special lecture for you talking about bodyplots. So I would like you to seriously go through this lecture so that you understand how to do bodyplots as an application for application in electrical engineering. So let's look at the two configurations and compare them. First one is a inverting amplifier, and the other one is a non-inverting amplifier where we apply the input to the positive terminal in this amplifier, the inverting amplifier, what we found out is the R in is equal to R1, and in R in is equal to R1 and R out is equal to 0. In case of non-inverting amplifier, R in is equal to infinite and R out is equal to 0 because it's driven by an ideal voltage source. Okay, so we would like to get a difference amplifier, which is subtracting the two inputs V1 and V2. However, we would like to get R in equal to infinity all the time. Okay, so how do we do that? So we can combine these ideas together, and here is a classic example. As I said earlier, innovation happens in steps. Somebody invents A, somebody invents B, and somebody invents C, and then somebody else comes in together, and then they put it all together, and then you have even a really awesome idea. So I'm going to show you how that happened here. And throughout this course, we will go into circuits in the same fashion, and I would intentionally show you old circuits and then we will identify which were the positives and negatives of that circuit, and then we will slowly chronologically how they developed and how researchers improved the circuits further. Let's come back to this particular amplifier. So we would like to, what is our objective? We would like to keep R in is equal to infinite. Okay, and we would like to keep R out is equal to 0. We would like large differential gain, and you want 0 common mode gain. Okay, so how do we do that? Of course, if we want R in to be infinite, then our best choice is to use this circuit. So I'm going to draw this slightly different fashion, and then you will realize what I'm trying to do. If you're watching this video, take a piece of, you should have a good notebook with you all the time. And then whatever we are doing in the classroom setting, you should also draw pictures in your notebook. And I stress that fact because when you see something, you convince yourself that you know this stuff. But when it comes to some kind of evaluation and you start drawing schematics or circuits on a piece of paper, you suddenly realize that, oh, I don't know where should be what should be this side. So it's important, as we are going along in the lectures, you also start drawing schematics in your notebook, and keep that as a practice, and it would help you tremendously. So this circuit I'm going to draw it a little differently, and in this case I'm going to draw again a resistor like this, and then I'm going to say this is ground. Okay, so you can see here, let's say this is VI1 and this is R2 and R1. So you can see this is a non-inverting amplifier, and the gain would be R2 divided by R1 times VI1. All right, now I'm going to draw another non-inverting amplifier, which looks which is drawn over here on the bottom. Okay, so this is Vi2 minus plus, make sure the feedback is negative. So here we got 1 plus R2 divided by R1 times Vi2. Okay, so I have two inputs plus Vi1 and Vi2, and then we got these two gained expressions, 1 plus R2 by R1. And now we are going to take a difference between these two using the difference amplifier that we just learned in the previous lecture. So how do we do that? We just connect two resistors here, and I'm going to draw this amplifier, a little bit fatter amplifier, just so that it's convenient. Okay, and then this is another resistor, and in this case, as we learned, I'm going to keep these resistors R4, R3, R4, R3. So the second amplifier, which uses op amp A3, this is op amp A1, op amp A2. The second amplifier uses will give you difference between VO1 and VO2. Okay, and the gain would be, as we derived earlier, R4 divided by R3. That would be the gain, and we have to of course take into account the this would be your negative terminal, and this would be your positive terminal for this difference amplifier. So from the previous expression, you can convince yourself the gain at the output would be R4. So this is plus minus VO. Gain would be R4 divided by R3 times 1 plus R2 divided by R1 and times Vi2. This becomes positive input minus Vi1. Okay, and as you can see, this is our differential input VID. Correct? So this works great, and so we got the since we have two stages of amplification, we get a large gain. So you can choose R4 divided by R3 to be 100 and R2 divided by R1 to be another 100. So you get gain of 10,000, something like that. So you can get a large gain, and even more if you can get more gain here. All right, and so the positive about this, as I said already, is you can get since there are two cascaded amplifiers, and that would lead you to large gain, which we desire. Also, another positive is Rin is equal to infinity, because you are going into an op amp, you are looking inside the op amp terminal. Okay. What is the disadvantage of this circuit? So this circuit has a very prominent disadvantage. If you look at our the particular example of common mode signal versus differential signal, and I would like you to follow my train of thought. Okay, let's take an example over here. We will only look at a non-inverting amplifier case. Okay, so I'm going to redraw the non-inverting amplifier case to make a point. Okay, so this is my input Vi. R2 and R1 plus minus. Now, if Vi contains VCM plus VID divided by 2, okay, think about this. What will this particular node be? Think about it. I'll give you 10 seconds to synthesize the information. The question is, if Vi is equal to VCM plus VID by 2, some voltage, what would be at the negative terminal of the op amp? Think about that for a second carefully. Since we have already done this before, we know that since there is a virtual short between plus and minus, the node negative terminal will also look like Vi, okay? And that will also have VCM plus VID by 2. The point I am trying to make is a non-inverting amplifier does not discriminate between common mode signal and differential signal if you are just using it this way, okay? So what this means is, for example, let's take an example. Let's say the common mode signal is 100 millivolts and differential signal is 1 millivolt for that matter. This 100 millivolt may be coming from the body hum, 50 hertz hum that you're riding, and then 1 millivolt is what actually you're trying to detect, okay? Now, if you apply 100 millivolt and then let's say the ratio of R2 over R1 is also 100, okay, then your VO1 will be 100 divided by 1 plus 1 times Vi. What is that equal to? That is 101 times Vi. Now we have a problem, because if you multiply 100 by 100 millivolts by 100, you're going to get 10 volts swing. And if your amplifier is, let's say, biased only from 5 volt to 0, you can immediately see that you cannot really get 10 volt swing. It will clip. It will clip to the maximum voltage, which is either supply voltage 5 volts or lowest supply voltage, which is 0 volt. If we go back to our original case, okay, so if you have a large common mode and if you have a small differential signal, similarly if you have a large common mode here and a small differential signal which is in the opposite direction, both will get amplified at VO1 and VO2. Subsequently, they will get subtracted in amplifier A3. However, if the gain in the first stage is high, let's say 100, and if the amplifiers A1 and A2 are operating from, let's say, smaller supply voltage, then VO1 and VO2 would clip purely because of the common mode signal. Now that's not a good situation to be in, okay? And that is happening purely because of this this connection over here, okay, the non-inverting configuration. So one cute solution to this problem is what I'm going to describe to you right now. And the solution happens to be extremely simple. What if we removed this particular connection, the ground connection from this resistor R1? What would happen? So let's analyze what happens if we do that. Let me clean up the schematic a little bit. And then we will kind of see what happens, okay? Rest of the stuff we can probably keep. Okay. So imagine we can do the analysis of this circuit in two parts using superposition, okay? We can just say, let me just apply common mode signal at the input and not apply differential signal, and let's see what happens, okay? So if I apply a common mode signal, at the input of VCM, and let's say I apply common mode of VCM over here, purely because that's the common mode signal, right? VCM is what we call that is same on both inputs, VI1 and VI2. Then we already know that the node, I'm going to use a different color. This node is also VCM. How about this other node? That will also be VCM, because the op-amp, the feedback around the op-amp creates virtual short between positive and negative. Now comes the interesting point. Earlier, we had a ground connection over here, and what that did is it caused a common mode current of VCM divided by R1 to flow through this circuit like this. VCM divided by R1, and that current totally flew through this ground connection that we had. Okay, so then you would have 2 VCM divided by R1, and everything else is the same as what we discussed. So that common mode gets amplified at VO1 and VO2. As soon as I remove this connection, something changes. And I hope you can observe that. What will happen is the following. If you look at this particular part of the circuit, the two resistors connected together, R1 and R1, I'm going to draw them separately over here on the side. So you have one resistor and other resistor, R1 and R1. And on each side of the resistor, we have VCM and VCM. The VCM could be moving around. But interesting part is, if on both sides of the resistor, the signal VCM is moving up and down together, okay, then there is no current that can flow inside these two resistors, right? Because delta V is equal to 0. So there will not be any current flowing through these two resistors, any common mode current flowing through these resistors. So coming back here, no common mode current flows through these two resistors, R1 and R1. And applying Kirchhoff's current law, then there is no common mode current flowing through R2, both the R2s, okay, which are in the feedback path for A1 and A2. So let me draw the picture again here. So there is no common mode current flowing through this R2, no common mode current flowing through this R2 also. As a result of which, the output will not have any gain due to the common mode stage, common mode current, common mode voltage. Let me repeat that. At the output, you will not see a component due to VCM input. Let me explain it again. What I'm trying to say is that since we removed this ground connection at the center here, the VCM appears across R1 and R1 over here on both sides, VCM. And since it appears across the resistor, there is no current. The same signal appears across the two resistors together in series. There is no current flowing through those two resistors, okay, because delta V is 0. And since there is no current flowing through that, by Kirchhoff's current law, there is no common mode current flowing through R2 and R2. And if there is no current flowing through R2 and R2, the output potential at VO1 and VO2 due to common mode signal is going to be simply VCM. And that's the part I would like to convince you. So due to common mode signal, let's use this VO1 is equal to VCM. Again, VO2 is equal to VCM. All right. So even though this VCM is moving around, the same signal will appear at the output without any gain. And this happened just because we removed that ground connection between the two resistors, which was over here. Okay. So once you are convinced with this, you can see that it doesn't amplify the common mode signal. And the second part will completely reject VCM because it will get subtracted out to the output, as we discussed earlier. What happens to the differential signal? So let's discuss that. I'm going to erase the. Now I'm going to apply to do our superposition analysis. Okay, let's do that. And I'm going to use a different color for that. Let's use yellow color. So if there is a VID divided by 2 applied here and minus VID divided by 2 over here. So the differential signal will appear across this resistor like this, VID by 2, VID divided by 2, minus sign due to the virtual short. And you can quickly see that the differential signal still flows through these two resistors. And you will see current flowing through these in this fashion. Okay, and you will see that at the output you should get 1 plus R2 divided by R1 times VID divided by 2, and at VO2 you will, this is what you will see here, and you will see 1 plus R2 divided by R1 VID divided by 2 minus. So the interesting thing of removing just this one connection is the common mode is not amplified by the first stage. However, the differential signal is nicely amplified. Okay, so this particular amplifier is used universally in many applications, and so this particular amplifier is called instrumentation amplifier. And one of the great things about this amplifier is if you look at the gain term, which I am highlighting over here in yellow and red, it's dependent on ratios of the resistors. So in terms of implementing on chip, this is perfect because as long as you make sure that the resistor ratio R4 by R3 and R2 by R1 is accurate, the gain of the amplifier is also very accurate. So that's another advantage that you have. All right. Next, I'm going to talk about integrator circuit using operational amplifier. What does integrator mean? Integrator means you look at, let's say here is a waveform that's going like this. Then integrator means you look at the area under the curve. Okay, you will take each value and you will integrate all of them, and then you will sum it up. So integrator is actually trying to figure out area under the curve. So for example, if I have, let's say I have a step input that goes from 0 to 1 volt. Okay. So when I integrate, I would just take samples at every point and I would keep adding. So if I integrate this, then I would have 0 to begin with. I'm just showing it separately over here. And then as soon as I hit my first sample, that will be 1 volt, then it will be 2 volts, then it will be 3 volts, and it will keep going on perpetually like this. So this would be integration operation. Okay, so we are simply adding each time point value, and that's what we call it as integrator. All right. So to implement this in op-amp, what we do is you draw the circuit first and then explain it to you. Minus plus, feedback is on the minus side, and here is our component capacitor. All right, and here is a resistor. So this is V input, R, let's call R and C. Let's say this is the node X. So you can quickly go through the expression. The capacitor in Laplace domain, we know that its impedance is 1 over SC. Okay, so V out over V in, you can convince yourself, is equal to the impedance in the feedback, which is 1 over SC divided by impedance input, which is R. This comes from the same expression as R2 over R1 that we did earlier, and the negative sign. So this R2 part is the impedance of the capacitor. Okay, and we can see that it is minus 1 over RCS. The 1 over S term represent integrator. Okay, and that is in the Laplace domain. Other way to look at this is also, you can say, you can just go through brute force differential equations that you are familiar with. So what would you do in that case? You would say, hey, V in divided by R is the current which is going to flow here, and that same current will flow through this capacitor, right? So that would be equal to minus C, and once there is current flowing through the capacitor, then your voltage will change. So C dV out divided by dt. That's the equation. I is equal to C dV by dt, right, for the capacitor. So if you look at this particular expression, then you can say that, hey, dV out by dt is equal to minus 1 over RC times V in. Hence we can say V out is equal to minus 1 over RC integration of V in with respect to dt. And this is the integrator operation that we are all familiar with. So this is all kind of review for you, but I'm going through it intentionally a little bit slowly in case your basics are a little bit rusty. So go through this one more time if you have forgotten. Now what does integrator really represent? 1 over S. So 1 over S represents at S equal to 0, this value goes to infinite, right? So the integrator represents pole at S equal to 0. Okay. So let me take a slight detour regarding poles and zeros. Okay. As I said again, if there is a pole if the expression has 1 over S plus A term, then at S equal to minus A, we have a pole. Because at that point, it will go to infinity. However, if you have term S plus A divided by something else, then in the numerator, then S equal to minus A, you have a 0. And what does 0 really mean? 0 means that at that point, the expression actually goes to 0. S equal to minus A frequency, expression goes to 0. Okay, so that's what we talk when we talk about pole and 0. That's what it means. Now the impact of I'm going to assume right now that you have done some sorts of bodyplot for all these. If you have not, don't be afraid. We are going to do a separate lecture for you as a review lecture for body plots. So go through that, and that should take care of the. I mean, it should be basics for many of you. But in case you have not done it before, you can go through the basics of the body plot. We will also provide some background material for the body plot. Generally, this is done in the previous classes, so we generally don't cover it in this particular class. Okay, so what is this is the ideal expression. Okay, V out over V in is equal to minus 1 over RCS. So here you're assuming that op amp has infinite AV gain. Okay. Now, if the op amp has limited gain, let's say AV, let's see what happens. What you can do is, I'm going to redraw the circuit one more time and go through the analysis in a little bit brute force manner so that you understand. Okay, so this is our V in, let's call this node X, and this is our V out. And this is the capacitor C, this is resistor R. So V in minus Vx divided by R is equal to Vx minus V out divided by 1 over SC. That's our expression, right? Also, we know that op amp has finite gain, which means Vx is equal to minus V out divided by AV. AV being the open loop gain of the operation amplifier. Once we know that, then we can substitute here, and then you can quickly substitute here, and I would like you to, I'll give you 10 seconds. You can pause the video here and go through the expression and write the expression for the V out over V in. Just substitution, solving the equation. Okay, so if you have got it right, then V out over V in is equal to minus AV divided by 1 plus AV RCS. Okay, so what does this look like? This expression look like? What is it telling you? Okay, so let me make a comparison. A comparison would be, simple comparison would be, compare this with something that's, I'm just using two different terms, 1 plus S divided by P1. This transfer function. Compare these two transfer functions. Right now we are ignoring the negative sign, okay, because a negative sign just gives you phase shift. Okay, so if you look at the gain, compare these two gains, then what is this telling you? This is telling you that our expression is going to look like, originally, if I compare these two, then ADC is equal to AV, that's our large gain, okay, and the location of the pole, now we have a pole location P1, which is equal to 1 over RC 1 plus AV. Okay. There is a reason I'm making this point to you. So it will all fall in place if you bear with me just for a second. Okay. So let's say we take a simple example of a resistor and a capacitor. Okay, R and C. So this is my V in and this is my V out. So in this case, you know how to derive this. V out is equal to divided by V in, that will be equal to 1 divided by 1 plus S RC. This should be pretty straightforward. So now we can compare these two and see what's really going on. We know that this represents a first order low pass filter, and what that means in frequency domain, we see characteristics that looks like this. Okay. So this particular expression would also show a characteristics looks like this in the body plots. All right. So let's go back and put all these things together on bodyplot. Okay, as I said again, the basics of the bodyplot we are going to go through separately with you. So what are we doing? We are plotting log of f, frequency on the x-axis. And on the y-axis, we are plotting the gain in dB. Okay, what does dB mean again? It's 20 log of the number, whatever that gain number is. All right. Now, if you look at the ideal integrator, the expression was 1 over S RC. If you look at the mod of that expression. Okay, what this means is there is a pole at 0 frequency, which means that at 0 frequency, which means as you keep going closer and closer towards origin, the gain is infinite. So this value will be infinite. And since we are plotting logarithm of f, generally we cannot plot origin on this particular plot, and what you would see then is your gain. I'll use a different color for the ideal body plot. Ideal integrator would look like this, something like this. Okay, and so S equal to, at frequency S equal to 1 over RC, gain is 1, and in dBs that would be equal to 0. So this is your 0 on the dB axis. So 1 divided by RC is the unity gain frequency. Let's modify this slightly, and what we will call, instead of f, we will call it log of omega. Otherwise we have to put 1 over 2 pi over here. S equal to j omega, right? That you know. All right. So this is the body plot or gain plot of ideal integrator. It just looks like a straight line, and the slope is 20 dB per decade. All right. Now, if you look at the effect of finite gain of the op-amp, then what happens? So we said that the expression is this right here, which is right here. So what this is telling you is that the DC gain or low frequency gain is equal to AV, which is the open loop gain of the amplifier. And that could be, in this particular case, I'm going to draw it in a green, and it looks like this, something like this. So this would be, the green is going to be our op-amp based integrator with finite gain. So this would be 20 log of AV. All right. And then this particular frequency that we are talking about would become then your first pole that you encounter, which is equal to this pole frequency P1, which is given by this particular expression. Okay, so we can say that this frequency omega here, this is equal to 1 divided by 1 plus AV times RC. That would be the first pole, P1. All right. And let's plot our simple RC filter on the same plot, and in a different color. Let me use a maybe blue color here, and you would immediately see that the DC gain here is 1, okay, 0 dB. However, the location of the pole is 1 over RC. So the location of the pole is same as earlier, and you can easily plot the curve then. It looks like this. Something like this. I'm drawing them separately just so that you can identify all three of them. So the green part would look like this. So let me recap again. The magenta curve, this one is the ideal integrator. And there, if it's 1 divided by SRC, the 1 over RC will represent unity gain frequency of that integrator. And at S equal to 0, you have a pole, so this curve will approach towards infinity as you go close to 0. And as I said again, we are plotting log of omega here. Okay. The green curve, which is shown over here, represents effect of finite op-amp gain, AV. And you can see that instead of going all the way to infinity, now you're limited to 20 log of AV. The 1 over RC part still stays the same, the unity gain frequency of this particular integrator. And the blue part, what I'm showing you is actually just an RC filter. The interesting part of RC filter is the DC gain is 0 dB. Okay. So there is no gain provided. The corner frequency is still 1 over RC, which is unity gain frequency. It's not really unity gain frequency, actually it's a pole frequency now, because as soon as you go close to it, it will drop by 3 dB. At the pole location would be still 1 over RC, and at that pole location, the gain would drop by 3 dB. Okay. So this is in a nutshell how we compare the three particular cases. One is ideal integrator, then the integrator with effect of finite gain of the op-amp, and the third thing we plotted a simple RC filter on top on the same lossy integrator. We call this a lossy integrator. So okay. Similarly, we can do analysis for differentiator circuit. So as you would have guessed it, whatever you do in the integrator, you flip the components and you should get a differentiator. And let's try that out and see what happens. So in this case, instead of a resistor, we would put a cap and then we would put a resistor here. Minus plus, remember minus sign over here, otherwise it will be a positive feedback. So this is capacitor C, Vx, R, and V in and V out. So I would leave it to you to prove it to yourself that V out divided by V in, first of all, is minus RC times S. So S is in the numerator, which means at S equal to 0, there is a 0 of this expression. Okay. So at S equal to 0, since the term is 0, the log term will go to minus infinity. We can also do the differential equation expression, and you will see V out is equal to minus RC times dV in divided by dt. And if we do the same finite gain analysis, you will see that V out divided by V in is equal to minus SRC AV divided by 1 plus AV. This is something that I expect you to do on your own, but I'm just writing the expression to make a point. And follow the same trick that we used before. Divide by RC. So what does this slightly complex expression tell you? This is telling you that the 0 is still at origin. However, there is a new pole introduced in this circuit, and that pole is at 1 plus AV divided by RC. That's the pole location, P1 in this case. And let's, as we did before, we will also compare this with RC network where this is V in and this is V out and this is a capacitor, resistor. So you can say that V out is equal to SCR divided by 1 plus SCR. And now we are going to compare all three of them on the same plot in the body plot. All right. So if you do the body plot now, it will look like this. And here we do log of omega. Omega is the radians per second frequency. It's plotted in the log scale, and the gain is in dBs, which is 20 log of gain. Okay. So if you look at the ideal integrator, we see minus RCS. Okay. So what we expect is, we expect at S equal to 0, there is a 0, which means, let's use the same convention, let's use this particular color. So this would represent ideal differentiator. So this is 0 dB. And as you would have guessed, at S equal to 1 over RC, you will have 0 dB frequency. So this would be 1 divided by RC for the ideal differentiator. Okay. So just this one particular intersection will define this differentiator circuit. As soon as we look at effect of op-amps finite gain AV, what we see is 0 is still at origin, so that part remains the same. However, there is a pole introduced at this particular frequency, 1 plus AV divided by RC. So what you would see then is, if you plot the characteristics, you should see something flattening out over here. Everything else remains the same. And the pole frequency is 1 plus AV divided by RC. And this is 20 log of AV, open loop gain. And the third thing we talked about is the blue part, which is lossy differentiator, something that looks like this. And then it will flatten out over here, something like this. The blue part is going to be, this would be your RC differentiator. This would be your op-amp differentiator, and the magenta would be ideal differentiator. Okay. So the concept of frequency response we're going to slowly introduce, and what I would expect, if these plots that I'm showing you, they are not making sense to you, then you should go through and review the body plot related material that we're going to give you. We will give you a online tutorial and also some links to very simple material that's easy to digest on body plots. Okay, thank you.